Hello everybody. Now in this video I will discuss first about instruction format and concept of operator, operand and register. And in the second phase I will discuss about different arithmetic moves. So first, what is operator? Operator is basically a character that represents an action. In mathematical notation, different operators we are using to represent various activities. Like plus sign is used for addition operation, minus sign is used for subtraction operation, multiplication sign is used for cross sign or is used for multiplication operation. Now, every operator needs some operand on which it will be operated. In computers, an operand is a part of computer instruction that specifies data that is to be operating on or manipulating. So, a computer instruction basically describes an operation, which consists of an operand as well as an operator. The most common fields in instruction format are an operation code or opcode that specifies the operation to be performed, an operand field that signifies the data on which the operation will be performed. But sometimes instead of this operand field, it will be treated as an address field. In those cases, the field is filled up with the address of the operand. And additionally, a mode field is there which specifies the way the operand or the effective address is calculated. Normally, we have three different types of organization, and based on that, we will discuss about the different instructions, like general register organization, single accumulator organization, and stack organization. So, first to start with general register organization. In this general register organization, we have two different type of instructions. One is three address instruction and one is two address instruction. In three address instruction, we have a provision to locate three different operands. And instead of two address instruction, you can have two operands. With the help of an example, I will show you how that three address and two address instruction executes. Suppose the information or about the equation is x equal to a plus b into c minus b. And remember, all these a, b, c, d, x are the memory locations. So how to solve this equation with the help of three address instruction? That can be shown here. Like add r1 comma a comma b. What does it mean? It means that the content of B memory location is added with the content of A memory location and the result is stored back in general register R1. In the same way, the second part of the equation is solved with the instruction sub R2, C, D. So the result of the subtraction part is stored in R2 general purpose equation. And you can see here in operand field there are three different operands in each of the instructions. Then at the end we can multiply those two values which are stored in R1 and R2 register to store that the result is X memory location with the instruction mul x comma r1 comma r2. Now we will see how the same instruction or the same equation basically can be solved with two addresses. Definitely, we need to incorporate more number of instructions if we really want to solve the same equation with two address instructions, because we have some limitations here. The limitation is we cannot add more than one operand in the instruction set. So these are the solution of two addresses with the help of two address instructions. Move R1A, then add R1B. So first, the content of A memory location is moved to R1 register, and that value is added with the content of B memory location. Remember one thing, any arithmetical operation can be done between two registers or between one register and one memory. Now, we have to move the result to R1. And in the same way, we can find out the result of the subtraction by moving the content of C memory location to R2 register and then subtract that register content from D memory location, and the result is stored back in R2. Now these two register content R1 and R2 can be multiplied together, and the result, the ultimate result can be stored back to X memory location. Now in the next, we can carry out our discussion about how to solve the same thing with the help of one address instruction and stack organization instruction, which is nothing but zero address instruction. So one address instruction means instead of 2 or 3, here we have a provision only to write one operand in the operand field. And in case of zero address instruction, there will be no operand in the operand. So let's see how this can be solved. In order to find out the solution of the same equation, first we have to load the data to accumulator. So accumulator will take a very important role in this register, in this one address instruction. The accumulator will take part in each and every arithmetical and logical operation. So first with load A instruction, we can load the content of A memory location to accumulator. Then we can use add B instruction to add the content of B memory location with the accumulator, and the result is stored back in the accumulator. Now, as we have only one accumulator in the system, so we have to print the accumulator. So the content of the accumulator, which is basically the result of the addition part, should be stored somewhere. We store T instruction. So the result of the addition part is stored in T memory. Again, the same thing can be followed to find out the result of the subtraction part. And after that, we will find out the result of the subtraction is found in the accumulator. Then the content of that accumulator, which is basically the result of the subtraction between C minus D, it can multiply that content with the content of T memory location, and eventually we will find out the result, which is stored in accumulator initially. But according to the given problem, the result can be stored in X memory location with the help of stored X instruction. Now the same thing is solved with zero address instruction. Now this is a special type of instruction where no operand is given with the instruction. Basically, the system stack is used here inherently. So before accessing the data, all the data should be placed into the stack to push operation. And if required, the data can be retrieved from the stack with pop operation. And always the operation will be done between top of the stack element and next to top of the stack. So to solve the same equation with the help of zero address instruction, first we will push the content of A memory location to the stack. Then we will push the content of B memory location to the stack. Then immediately we have to find out the addition operation between these two. That's why add is used here. And anyone can notice that add instruction does not require any operand in the operand field. Only add is enough. That's why it's called below add instruction. So whenever we are giving this type of instruction, always the system access the system stack and the top of the stack element is popped out from the stack and will be stored in the intermediate box. Then the next to top of the stack element, which is now become the top of the stack element, is popped out again. And the operation will be going on between these two values. And after the operation, the result is pushed into the stack. So after this add instruction is executed, basically the top of the stack element indicates the result of the addition part. The result of the subtraction part can be obtained with the same procedure. Like first push the content of C memory location, then push the content of B memory location, then execute the sub instruction. So after executing the sub instruction, we will get the result of addition and result of subtraction. Then we will multiply these together to find out the ultimate result. And ultimately the result is stored back in X memory. So the system stack content is shown in the figure. Initially, the system stack is in. When push A operation is executed, the value of A is pushed into the stack. Then value of B is pushed into the stack. Then these two are added. So the result is stored back into the stack. Then C and D is pushed into the stack. The operation is carried out between C and D. The subtraction operation is stored back into the stack. Then ultimately the final operation is carried out. Next, when all the result is popped from the stack will become empty. Now, for performing these operations, we require some register, which is basically the fundamental building block of memory. Registers are able to store data temporarily. Normally, all those registers are made up with flip-flops. An n-bit register is capable of storing n-bit binary values. Normally, two different types of registers are found in the system. One is called general purpose register. Those are used to store data for intermediate results during the execution of the program. And some of the registers are used for special purpose. Those users do not access those registers. These registers are only accessed by the computer system, like program counter, memory address register, memory data register, instruction register. So, special purpose registers has fixed activities and fixed responsibilities. Like program counter always stores the address of the next instruction. Like in the next part, I will discuss about the different addressing modes. The operation fields or opcode field of an instruction specifies what kind of operation to be performed. There are various ways to execute those operations. The way the operands are chosen during the program execution is dependent on the addressing mode to the addressing mode specifies the rule for interpreting or modifying the address field of the instruction before operand is actually referred. Different types of addressing modes are used. Normally, this is the instruction format used for addressing. We have three different fields. One is opcode field, one is mode field, one is operand or address. We have talked about opcode field and operand field earlier. Now, mode field has a very specific task. It signifies the addressing mode, and based on those different addressing modes are executed, and eventually the effective address is considered for the percent. So these are the different addressing modes available for the computer organization. Implied mode, immediate mode, register, direct mode, register, indirect mode, auto increment and decrement mode, direct address mode, immediate address mode, and different types of displacement address. Now first to start with implied address, implied mode. Here in the implied mode, the operands are specified implicitly with the instruction. Like CMA, complement accumulator. Add the instruction used in stack organization. CLC to reset the carry flag to 0. Suppose CMA, whose meaning is complement accumulator. So whatever the content of the accumulator is, that is complementary. We will find out the one complement of the accumulator. So the action is inherently specified within the instruction, and no operand field is required for this. Next, in the immediate mode, the operand is specified within the instruction itself. The immediate mode has an operand field rather than an address field. Like add 37. That means the value 37 that is represented in hexadecimal is added with the accumulator content. Whatever the current content of the accumulator is, that content is added with 37 and the result is stored back in the accumulator. So immediately within the instruction, the operand is supplied. Next, register direct mode. Here the operand is placed in some general purpose register. That can be an exit register, that can be an exit. So the data is in the register that is specified by the instruction. That is called register direct mode. It has some advantages. Like the instruction are become shorter. and first memory access to the operands as registers access time is very less. So these are the examples of register deduction. Like add R, add B, etc. So whatever the content of register R has, it is added with the current content of the application. The only disadvantage of this mode is the address space is very limited because as we have a very limited amount of general purpose registers in our. The actual data is stored in those registers which are specified in the instruction. Next, register indirect mode. Here, the register used in the instruction actually holds the address of the operand. That's why it is called register indirect. The address of the data which is used for execution is stored into the register, and that register is specified in the instruction. So with the help of that register content, system is ultimately will be able to access the data in an indirect way. That's why it is called register indirect. Next, auto increment. After accessing the operand, the content of the register will be automatically incremented to point the next consecutive memory location. So one of the very useful example of this auto increment mode is program counter. Normally, program counters hold the address of the next instruction fetched. When actually the next instruction is fetched by the system, the value of the program counter is automatically incremented by 1 to point out the next instruction. Next, auto decrement mode. It works just in the reverse way of the auto decrement mode. The very good example of that auto decrement mode is the system stack pointer. Next, direct mode. Here, the address field of the instruction contains the effective address of the operand. It is also known as absolute addressing mode. Suppose the example is add R1, 5396. Here 5396 actually refers the memory address, direct memory address. So if the system is going to that 5396 memory location, it will found the data over there, and that data can be fetched to add with the content of R1 according to the given. Next, indirect mode. Here, the address field of instruction gives the address where the effective address is stored in memory. So here, two different references are required. In the first reference, the system will able to get the effective address, and in the second reference, ultimately the system will get able to find out the data expressed in the effective. So the address field specified in the instruction is basically the address of the operand. That's why it is called the indirect. Next, we will discuss about different displacement address mode. Here, address field holds two different values. One is the base value, and then the displacement. So, different versions of displacement modes are relative address mode, base register address mode, and index. In relative address mode, the content of the program counter is added to the address part of the instruction to obtain the effective. So actually, the effective address is the of the operand is obtained by adding the content of the program counter with the address part of the instruction. So the instruction consists of an address part in the history. And when the actual effective address is calculated, that address part is added with the current content of the accumulator of the program counter to find out the actual address of the operand. In case of base register address mode, the content of the base register is added to the address part of the instruction to find out the address. And in the index register address mode, the content of the index register is added to the address part of the instruction to obtain the effective address. So the effective address is obtained by adding some the content of some additional register, and those registers content are added with the address part that is specified in the instruction. That's why these are called relative addresses. This is the end of today's video.